I will talk about deep learning and deep fuzzy networks. So, since this involves kind of understanding about, the learning and why learning and what learning uh, achieves, right? So we'll slowly try to cover these terms, and then we'll move to the main topic, right? Main contributions, which I would like to share with you all. All right, so you see, deep learning word is very common nowadays, very commonly used and very widely discussed. So let me tell you quickly, the deep learning is not new. The concept deep learning is right. It was uh, proposed. It was coined basically by Ivanko and Lapa in 1965. However, due to lack of the tools to deal with the deep learning network, right? The learning was not very efficient, right? So these tools were not very efficient. That's how the deep learning was not very popular. It was in 2006 when Hinton, Bengio, and Lacun came together uh, to showcase the application on deep learning, right? And since then, you see, deep learning was becoming very popular. And nowadays, you see, the deep learning concepts are applied everywhere. So when we talk about this word deep learning, you see, deep is one word, another word is learning, right? So what is deep and what is learning? Let us quickly go through, right? So before that, I would like to just mention here that you see, the deep learning and machine learning words are very commonly used by the research and academic community. All right. So I hope I am audible. Am I audible?
Yes, sir.
Yes, sir.
All
Audible.
right. All right. So please keep just giving some signals so that I should not be. It shouldn't be one way, right?
Yes, sir. Sure.
Otherwise, it would be like I kept on speaking, let's say, and because of the poor network, I may not, my voice may not be transferred. Okay, so deep learning, machine learning, right? So we will also try to understand what is the difference between the deep learning and what the machine learning. Although both the words are, the part of AI as a whole. So if you look at the search trends, so you see we have the machine learning and the deep learning. Both the words have almost similar trend, right? But you see the quantum is different. And if we look at this carefully here, we see that the deep learning word exists in literature in between 1960 and 65, right? So you see, as I mentioned, the deep learning technology, deep learning concept, deep learning network was proposed initially by Ivanko and Lapa in 1965. All right. So learning is everywhere. This machine learning and deep learning, both the words involve learning. So what is that which we are going to get by learning, right? And what is basically why it is needed. So let us first understand quickly. So you see, we all right from the childhood, the moment we start understanding things after birth, we start learning either knowingly or unknowingly. Okay, and you see, some people learn faster, some people learn comparatively slower, and likewise. So, based on the learning capacity, learning capability, we rate the individuals in terms of the intelligence, right? So, if somebody learns faster, right, uh, we can say, okay, this person is more intelligent, right? So learning results basically intelligence, either, just for the sake of understanding, we can uh, write this, we can state this, but otherwise, you see what happens, the learning, the performance in learning is the measure of AI. Sorry, not AI, measure of intelligence, I, right? So, and it is because of the natural intelligence in living beings, right? So now we need to understand here that you see, learning is very, very important measure of one's intelligence. If one can learn faster, one is more intelligent, right? And if we are comparing the intelligence, we can accordingly compare. So similar to the human beings, we have animals. So we can call that in other living beings we have natural intelligence, of course. And this is because of what? This is because of the biological neurons, the bunch of biological neurons, right? That God has gifted us, right? And because of that, we have the all living beings have the capability of learning. The grade may be different, of course. One can, I mean, animals, some of the animals even can learn faster or maybe slower, but depending upon the learning capability, learning, performance, we can grade their intelligence. All right. Now, why are we discussing this? Let us understand. So, we are discussing this because we want to understand and we want to create artificial intelligence, right? Our intelligence artificially. Why do we want to do? See, we all are interested in automating everything around us in order to increase the productivity in industry, performance in the systems around us. So gone are the days when robots were asked to perform certain tasks, right? For example, if I have, let's say, a manipulator, a robot, or any device which takes the order and does the job for me. For example, if I ask my robot, okay, go and get a glass of water, the robot will go and pick the glass of water and will hand it over to me. But after a while, I may not be interested that much. I may be interested in something more. Many a times, since the robot must have done the same or similar kind of tasks again and again. So I must have thought about of a robot, that why not robot is understanding me, and whenever I am interested in water, a glass of water, the robot should deliver me. That means we are interested now that my robot should understand what I'm interested in. Whether I'm interested in a glass of water or even if I'm present, I may not be interested in the glass of water, right? Even if I call, I not all the time I'm interested in the same kind of task. So in nutshell, what I'm trying to say here is that we are all interested in embedding intelligence, are interested in the intelligence artificially in the systems around us. Why are we interested in this? Just because we want, one step ahead for our devices, for our machines, for our systems around, right? That okay, I should not instruct unnecessary system by observing the behavior, observing the conditions, observing the environment around, should take the decision automatically. So it's basically the one step ahead in automation, right? So embedding intelligence is kind of it's an step in the automation process, right? So how can we do that how can we achieve intelligence in non-living being systems? Non-living being systems means the machines, the robots, manipulators, right? So this is possible. The a portion of the intelligence, partial intelligence is possible to be embedded in the machines, or in short, the non-living being systems. All right, how can we do that? Right, that is the question. So if we are able to do that much, this means we are creating the intelligence artificially. All right, and the know-how of creating the intelligence artificially is coming under the faculty of artificial intelligence. All right, so that is what is our aim. And before creating, before developing the artificial intelligence, we should know what is artificial intelligence. All right. So let me tell you before going ahead, is AI, the artificial intelligence, basically the R, I would say, intelligence artificially can be achieved through various AI agents. There are n number of agents that facilitate the embedding of the artificial intelligence in non-living being systems. So I hope I have communicated this very well. We can discuss this at the end of this discussion if there are any questions. All right, so the main job of the agents are what? The main jobs of the agents, AI agents, are to facilitate learning of the non-living being systems. So if I have, let's say, a robot, I should have some mechanism which facilitate learning. And how does this learning happen? Similar to what? Similar to how we learn, right, from the past experience. So the machine also learns from the data, from the past data. And then next time when it is learned, then next time when the machine is kept under observation, the machine takes input, and then accordingly it tries to take decision. Right. So this is how the non-living being or the machine is trained through AI. So more is the experience, that means more is the data, better is the performance of learning, or better is the performance of the machine in terms of the AI or the decision making. Right. So this is what we must know. Now, as I already mentioned, we have n number of AI agents which could facilitate the AI, the embedding of the AI in non-living being systems, right? That means the robots or any other machines. These agents could be either neural network, that means the artificial neural network, fuzzy systems, swarm-based intelligence, swarm intelligence, or swarm-based intelligence, statistical learning, and there are so many. Rupture theory, n number of agents are available, right? So depending upon the uses, depending upon the suitability, we can pick any of the agents, AI agents, and try to develop the intelligence and embed into the machine, the robots, which we are interested in. And then we get the AI enabled system. So let us now talk about the one of the agents that is very popular nowadays is artificial neural network. You see, when we talk of the artificial intelligence, so at the engineering point of view, it was in 1937 when Turing machine was developed, right, by Alan Turing. And afterwards, there is another landmark. Just after that was the development of the conceptualization of ANN, artificial neural network, by McCulloch and Pitts. One of them was biologist, another one was the mathematician. Both joined hand together to develop the mathematical model of the biological neuron, right here. So we must know that in our brain, right, normally we have hundreds of billions of neurons, biological neurons, right? And for carrying out certain tasks, no less than tens of thousands of biological neurons are connected together to take up the task, right? But here we have a very single, the unit cell of the brain, that is the neuron, the biological neuron. Here, this is the biological neuron, and these two gentlemen, the researchers, developed the mathematical model of it. So let us now quickly go through the essential parts of the biological neuron. We have the dendrites. Dendrites takes the inputs, and all the inputs are summed up and passed through the cell body. You can see the cell body here, and then depending upon the property of the fluid present in the cell body, the threshold is developed, and based on the threshold, a spike is created on the axon. So this is how the spike is created, right? So there is no analog voltage, that is the analog signal, that is the outcome of the biological neuron. It basically gives us the spikes, and in 1 second, not more than 100 spikes could be achieved out of the biological neurons on the axon. An axon is connected to the axon terminals, right? The same voltage signal is now available to the axon terminals. This is also popularly known as axon buds, and these buds are further connected to the next level of the neurons through the dendrites, their terminals, and in between the axon terminal and the dendrite terminal, we have the soft connection, right? And this in between the soft connection, we have the neurotransmitters, and the density of the neurotransmitter will decide how much signal which is present on the analog, the axon bud can transmit to the dendrite of the next neuron, right? So that's how the concept of weight comes into picture. All right. So now you see the mathematical model of the biological neuron, that means the artificial neuron. So we see, similar to this, we have a cell body here, right? Similar to the cell body of the biological neuron, we have the cell body here. You see the cell body here, right? So now we have the cell body, and then we have the dendrites, the input nodes. So these are the input nodes, okay? And this is similar to the dendrites. Now we have the activation function here, which actually represents the property of the fluid present in the cell body, right? And that will decide the threshold, right? And then finally we have the axon here. This is axon, right? And based on the activation function and the inputs and the bias here, which actually decides the DC level, right, of the signal. So we have basically the output available on the single neuron. So in short, I am able to now communicate to you as to how an artificial neuron out of the biological neuron, right, So artificial neuron model mathematically has been suggested. And you see, as I mentioned, for carrying out certain tasks, around tens of thousands of neurons join hand together to carry out the particular task. Similarly, the artificial neurons also, the join hands, right? They are interconnected together in different topologies to carry out certain tasks. So you see, here we have out of so many configurations, so many topologies, we have one of the topologies is feed-forward, very simple topology, right, where the neurons are interconnected. So if this is the kind of network that is available, right? So we call this layer as the input layer, and the final last layer is called the output layer. And in between the input and output layer, we have the layers of the neurons, right? These are the hidden layers. So here in this case, we have three hidden layers, right? Here we have three hidden layers, right? So these are the terminologies that we must understand. So everything is fine up to this level, right? But since we are, we have been studying the neural network for quite long time, and we have been very familiar with the backpropagation algorithm, which is being to train the network, to develop the network, right? So there is no issue at all as long as things are at the shallow state. But you see, when we deal with the problems or the processes that are very complex, that are suffering with lots of uncertainties, and we would like to deal with that kind of process, or we would like to model that kind of process, we must have more number of layers than normally we have. So up to 2-3 layers, hidden layers is fine. But when we increase the number of layers, we start facing certain issues. What are the issues that we normally face here is the vanishing gradient issue, right? So vanishing gradient issue backwardly, when the gradient is minimized, or the getting vanished, the learning of the initial layers, then the initial weights are not happening, and thereby it will be causing the inaccuracy or the loss of the performance, right? So vanishing gradient is one big issue which normally neural network suffers with. The neural network with more number of hidden layers. All right. So this is all right. We have now come to know the main issue of vanishing gradient. The another issue, which is which normally we face in the network which is trained by the backpropagation, is the local optima, right? So we normally don't achieve here the global optima. Why do we do that? Why do we get this kind of issue? Is because when we train this network, we initialize the weights initially, right? And it is randomly. So every time whenever you are training, the weights are randomly picked up, and it is now it depends upon the fortune. Maybe sometimes your weights are good, you will take lesser time to get this trained. Otherwise, you see, you may be taking some other initial weights which may be taking even longer, or even may not be conversing so easily, right? So these are the main issues that we come across, but only when we have the problems with either the processes with higher uncertainties, or the complexities that are present in the process, right? So unless these are the kinds of things, like we may have some image related problem in computer vision, where we have lots of uncertainties present in the image for classification, or maybe the ambiguities are present, some uncertainties are present, right? So then we need more number of hidden layer. Otherwise we don't. If the processes, if the system is that we would like to model is not very much complex, then we normally do not require the more number of hidden layers. So now you must understand at this point that back propagation is not very helpful when we have more number of hidden layers. So when we say more number of hidden layers, it means more than 3 number of hidden layers, 2 to 3 number of hidden layers. Up to 2 to 3 is fine. We can somehow manage the learning of the network. But when the number goes beyond that, we require some mechanism which would help us in getting the network, such network developed. So when we have more number of hidden layers, this means, you see, if this is the kind of network, right? And if we are inserting more number of hidden layers like this, you see, so what is happening? The number of hidden layers from 3 to now is 7, right? So what is happening now? The number is 7, right? So the network can be considered as deeper network, right? Deeper means when we have more number of hidden layers, the network is considered to be deep, right? So when we have such a network, how do we go for learning? What are the mechanisms that are available for learning? So the learning mechanism that is that helps, the processes that helps us in learning such a network is called deep learning. The learning process is deep learning, right? So as I discussed just before, the limitations of neural network, right? The normal neural network is this, right? Local optima was the problem. And then you see the initial, random initialization is the problem, right? So all of these basically could be very well managed when we go for some other learning mechanism apart from or instead of the back propagation algorithm. So deep learning is the solution which nowadays is helping in learning the deeper networks, deep neural networks, right? So as I mentioned, the just for our understanding, right? So when we have any complex system, right? Let's say we have a very complex mechanism or complex process, right? And when we increase the number of hidden layers, right? These are the, let's say, hidden layers in the network. So all the successive hidden layers are actually learning the hierarchical, the features, right? So we can see here, if we have only one network, the feature would be like looking like this, and it could be more refined if we keep going ahead, right? So this is just a representation. Don't think that this is the actual images that we have got out of that. So this is just just for the sake of understanding, these images were linked with the modules. All right. So deep learning, when we talk of, right, it's a strategy. Basically, this has nothing to do with only the neural network. It could be any network which could be trained with the strategy, with the deep learning strategy. All right. Let us now understand some of the deep learning or deep networks. When we have the deep network, which is consisting of the neurons, right? We call this as the deep neural network. Please understand. Deep belief networks, right? So similarly, when we have neural networks present, right? Neural network with more number of hidden layers, it is called what? The DNN. And DNNs are also of different types, right? It could be if it has the memory element attached to it. So this is LSTM, right? This could be CNN, right? If it is, it has the, it is used for computer vision purpose normally, for filtering, pooling, and all, and classification. So CNN is also one of the kinds of DNN, deep neural networks, right? So apart from the neural networks, we can have the deep fuzzy nets, right? When we have the network, the fuzzy node networks, right? We can call this as the deep fuzzy nets. So likewise, we can have any network. So here you see the deep learning strategy that I will be discussing, right, can be applied to any non-linear net feed forward network, right? It could be even other kind of network, not necessarily the feed forward network, right? So, and the nodes here are non-linear nodes. This node could represent, could be represented by either neuron or even a fuzzy model, right? So here in one of the research themes, we have replaced these nodes by fuzzy models, and we have seen a very good performance when we obtained the model that is performed. The performance of the model was quite encouraging. So I will just go through this after this. Let us quickly go through the history of it. As I already mentioned, that we have this deep learning, model which was proposed and conceptualized in 1965. This was exactly at the same time when Professor Lotfi Jade conceptualized the fuzzy system, right? And this was the actual network. Please understand, this was the actual network, right? Which was proposed by the Ivanko and Lapa in 1965, right? So this is what I was just mentioning, that backpropagation network, although it was existing that time in 60s, but it was not very helpful. So for getting the parameters of the model, which was proposed by Ivanko and Lapa, the statistical model, statistical learning was used, not the backpropagation algorithm. And it is the time here in 1986, the backpropagation was matured. So since then till 2006, the backpropagation was the only solution, right, for getting the model, ANN-based model, right? So backpropagation was very widely used till then. Afterwards, after 2006, since Bengio, Lacun, and Hinton, they developed the deep learning strategies, and this could be very helpful for developing the ANN-based models, right? So you see, we have seen the deep neural networks, right? And this is how it could be understood. As I already mentioned, that every successive layer is hierarchical representation of the features, right? And here you see the Hinton, Bengio, and Lacun, right? These three, you can see the work of these three researchers. You can just go on the internet and see that, right? Now, the learning strategy here is in two stages. First stage is the course learning, and second stage is the fine tuning, right? So course learning here involves, you see, the autoencoder, right? So we have this is unsupervised strategy. So we develop autoencoder first, and then for each and every layer, the autoencoder is developed, and then we stack them together finally, and then we use the level information to develop the overall. We fine tune the network to develop the overall model of the process or the system, right? So this is how it is done. And even if the noise is present, the autoencoders help us in managing the filtering of the noise, right? You can see here. So, this noise part also is getting handled very well, right? Through the denoising autoencoders. And then we stack them together. You see, we stack them together and fine tune this. So fine tuning is the next stage where we use the class levels, and this is a supervised way of managing things, right? Where we use the class levels through classifiers. This classifier could be soft max classifier or Canon classifier, or maybe a support vector machine based classifier, or maybe any other classifier, whatever classifier that you would like to use. And as I mentioned, deep learning involves two stages of learning. First stage is the course training or course learning, where any strategy of learning the autoencoder will help. Even it could be the backpropagation algorithm as well. So we have the backpropagation algorithm, we can use it for training the autoencoder weights, and we can keep these weights and for each and every successive hidden layers, and then after stacking them together, we can use these weights as the coarse trained weights. And when we use finally the class levels, we attach the classifier, and then we can use for use the training, use the fine tuning training. All right. So this is all is fine, but now you see, as I mentioned, that what if we replace the neural network by a neural node by a fuzzy model. So this is what we have done, and for that we initially found the motivation. The motivation could be, you see, the fuzzy models basically are very helpful, as all of you may be aware, that it handles a special kind of uncertainties, the uncertainties due to vagueness, ambiguity, imprecision, and all, which no other mechanism deals with. So what if we have any data where the ambiguities, vagueness, and imprecision types of uncertainties are present? The fuzzy could only be the solution, right? So here we have, demonstrated in our lab that you see, when we have a fuzzy version of a network, right, we see the training error is much lower than the ANN. Similarly, the testing error as well here. And this is because you see we have more number of parameters available to tune, to adjust, and this is again at the cost of the computational complexity, because you see when we have more number of parameters, then of course we need more time, more efforts to train or to tune or to adjust these to a suitable value appropriately, so that it gives the better performance. But you see, this can be utilized, this can be used, where we are interested in very high accuracy, like for example, for medical applications, we are not bothered about the expenses. So at that places, that situation, we can use such kind of network where we are interested in the better performance, at any cost, right? So similarly, we have a general, training model, and here is the motivation that why are we interested in deep fuzzy network. It is because the uncertainties due to vagueness, ambiguity, imprecision. These three are really important in the data if these are present, and fuzzy will be very helpful. Otherwise, the systems, the models suffering with this kind of uncertainties could never be managed, could never be modeled. With better performance. And then the second performance here is, second motivation here is you see, you can very well understand if you open the network, right, very easily, because let's say we have a DNN, right? DNN will just be having the matrices of the numbers, right? The arrays and all. Whereas if we have a fuzzy model, it would be having a set of rules, so we can interpret what is happening at each and every node. Similarly, you see, if let's say we want to add some expert's knowledge, we can very easily add in terms of the rules to the deep fuzzy network. So that way, this is very helpful. The fuzzy system is very user friendly and very well performing in cases where we have a very complex process and and the situations where the uncertainties due to ambiguity, vagueness, imprecisions are present. And that way, you see, this is going to be very, very beneficial. And here we have some functions that were modeled using the fuzzy version of the network, right? And we see the performance is much better than its neural network counterpart, right? So we can see the fuzzy has better error than the neural network, right? ANN. But at the same time, I would like to tell you that we have, you see, the efforts that are needed is more. So it is expensive, and expensive in terms of the time and the space, right? So that way we need to understand, right? But there are places, there are situations where we are not caring about the expenses, and there it is going to perform much better, right? So with this, I would like to stop here. And if there are any questions, I would like to take up. You see, this is the general network, the fuzzy network model, right? The architecture which could be used for training the network. Okay, so thank you very much for listening to my lecture. And if you have any question, I would be glad to take up.